you know how electromagnetic induction works, transformer should be easy because it's basically an application of that. So the way I'm going to start is just looking at when you have a battery and you close a switch. Now you know already that transformers have coils on one side, coils are a coil. Okay, let me just start again. Now that you understand electromagnetic induction, transformers should just be an easy application of that. So I'm going to look first at when you have a battery and you switch on the battery. This is exactly what we had in the first chapter when we had a current, we had a coil, and as soon as the current flows in that coil, there is a magnetic field that is created. Now, remember, there will not be a EMF induced in anything close to this coil if there isn't a change in the magnetic flux. Remember, that is the important, very important part. So only while this magnetic field is being created will there be a change in the magnetic flux here. And also this coil that is now next to it will also experience that same change in magnetic flux. So if this coil experiences a change in magnetic flux, then there will be an EMF induced, and therefore there will be a current a current flowing. Now what you will see here on your ammeter is that it will just quickly go to one of the sides. Let's just say positive, it will go positive and back to zero because now the field has formed already, and it means that there's no change. The only way you can get this field now to change again is if it goes away. So if I open the switch, these field lines are now going to disappear. And as they are disappearing, again, there is a change in magnetic flux. And if there is a change in magnetic flux, there will be an EMF induced, and therefore there will be a current flowing. So if you switch it on, it will deflect in one direction. If you switch it off, it will deflect in one direction, going back to zero each time. But now to keep on forming an alternating current here, I would have to switch this on and off, on and off, on and off all the time, and that's not really very helpful. So what we are going to do instead of having a battery here is we're going to use something that switches the current on and off for us itself. And you will know that that is an alternating current. So what we will have on the one side is an alternating current source. And remember, the symbol for an alternating current is just that little waveform there. So there's an alternating input. So it means the current is going in, out, in, out, in, out, which means there's a magnetic field here or magnetic flux that's going to go one direction, other direction, one direction, other direction, constantly changing. So there's a constant change in the magnetic flux, and therefore this coil will experience the same constant change in magnetic flux, and there will be an EMF induced, and there will be a current flowing out on this side, which can make our light bulb shine or anything else. Now, to name them, you will see the one that comes from the power source is always going to be the primary circuit. So the primary coil, the primary voltage, the primary current. The one that goes to your appliance, so in this case our light bulb, will be the secondary current, secondary voltage, secondary number of turns. Remember, the symbol for turns is just an N. Now the way in which a transformer works is very important. It needs alternating current because it needs this change in magnetic flux for an EMF to be induced in this secondary coil. But also, it won't make sense if they have the same number of windings, because the whole point of a transformer is to either take our voltage down from a high one to a low one, or up. And we're going to name the transformer exactly according to that. So if I have 200 volts on this side, but I want to charge my cell phone, and my cell phone only requires 20 volts to be charged, this coil might have 100 windings, so N is going to be equal to 100. Now remember, please label them when you read your question so that you don't mix up these numbers. Sorry. Now, if I want to change the 200 into 20, I need to change the 100 into 10. So the ratio, and you've done this in detail, I'm sure already, between the coils and the voltages will be exactly the same. So you get this equation on your information sheet. The number of windings on the secondary coil over primary coil will be equal to the voltage, the ratio of the voltage on the secondary coil to the primary coil. Please, please, please just read your question nicely, because often they give you a question like this and they swap it around and they say ratio, and then you guys go and give an answer. Read the question and please give an answer according to what the question is asking. If they ask for a ratio, give a ratio. If they ask for primary to secondary, then it's not like it is on the information sheet. Then you must give it primary to secondary. Now you will see that all of these refer to an ideal transformer. Now, what do they mean when they say an ideal transformer? That means all the power that comes into your primary coil is distributed to your secondary coil. It isn't an ideal world because it's not really going to happen. So it means that your transformer is 100% efficient. So there could be an efficiency question coming in this section, because they can tell you that the transformer is 90% efficient. So if it's 100% efficient, you know power in is going to be equal to power out. Now in this case, remember, power in is primary, power out is secondary. And you know from electricity that power is equal to voltage times by the current. So that means Vp times Ip is going to be equal to Vs times by Is. Now, if it's not 100% efficient, you just need to remember that the power in will be maybe just or the power out might be just a portion of the power in. So then you just work with your percentages and you solve the maths there, which you guys are fine with, I think. Please remember that it doesn't have to be iron core. This is an iron core transformer, and that is what is mentioned here in the SAP. You will see it says there, explain the basic principle of a simple iron core transformer. So this is exactly what that is. But we don't have to have an iron core. We can just have one coil next to another coil. But remember, the one will have a power source, and it has to be an alternating power source. Then there will be a flux created here that is changing. And then just remember that this secondary one, where your light bulb is, or your voltmeter or your ammeter, will experience that same change in flux. And therefore, there will be an EMF induced in the secondary one, and a current will start to flow. And that's transformers. Right. Okay, now we're quickly going to look at why do we need transformers so much, and how does ESCOM get the energy to us? So if you look at the power again, I'm just going to make it a little bit smaller. So here we've got, I should have given you a nice diagram, but I'm just going to draw. There's the factory power station, not factory power station. So ESCOM produces electricity for us, but now they need to get it to our houses. And we already know that they're going to use generators, and generators always gives us AC current, but we need AC current anyway, or I shouldn't say AC current, alternating current, or AC, because we need to use transformers. Now, why do we need to use a transformer? Because we want the voltage that travels to our houses to be as high as possible. Why is that again? Now let's look at power. Power is equal to voltage times by current. And if you understand electricity well, you'll know that voltage is energy and current is the electrons, the charges that's moving. Now, if I have a lot of charges moving, there will be a lot of friction and therefore a lot of heat energy lost. But if let's put values in, if I have 10 electrons, each carrying 100 joules of energy, I will be able to transfer 1,000 watts of power across. Now I have 10 of these particles moving. So if I want less particles, but I still want the same power, let's just use color. If I now take one electron, that one electron needs to carry the whole 1,000 joules, but that means that we only have one electron moving in our circuit. So less friction, less heat losses. So we want our voltage to be as high as possible so that our current can be as low as possible so that we don't lose energy, too much energy as heat due to friction in these wires. So at ESCOM, they use a step-up transformer. We've just discussed transformers. They need a step-up transformer, and therefore they have to produce AC because transformers need AC, as we just discussed. We step up the voltage to be transferred in the wires, no energy or low as possible energy losses due to friction, and then we need to step down the energy with a step down transformer again, not the energy, kind of the energy, the voltage that reaches the house, and we need to use the step down transformer there. So that is why we need to use high voltages and low currents for the transmission, because we do not want lots of particles running in these wires causing lots of heat to be lost. Now your favorite part, let's get to the graphs. Clean up there quickly. I'm going to do it looking at the generator type movement again. So if you remember now from induction, when you had an area or a coil or an armature, it doesn't really matter what it is. If you look at this, why do they say theta is 0? Remember, it's because the angle between the normal to the area and the magnetic field that they give you here from the left to the right is 0. Remember, it's the normal. Now here, the angle is 0, and because it's cos theta, if you want to use the math, then it's going to be a maximum flux. You can also just look at the diagram or think about it logically, because you can see in this position, all the lines or a maximum number of lines will be crossing, that will be going through that area of the coil. Then as it turns, we get to this position here, which means now I'm at 90 degrees. So there's my normal, there's my magnetic field. So there's a 90-degree angle, and there my flux is going to be 0. Cos of 90 is 0. Back to maximum, back to 0, back to maximum. We've done this in detail before, but now we want to see how does this lead to the graph. Now I always start by drawing the flux graph. So we want to have a flux graph because that's the one we can figure out logically for ourselves. So a flux graph for this movement, for instance, if we look at this first diagram, that point there will be a maximum. Whether you start at positive or negative is not really that important because you don't really know, as long as you then follow the same rules from there on. So maybe the question tells you, maybe it doesn't. If it doesn't tell you, just make sure that you start at a maximum. So we start here at a maximum flux. Remember, flux and flux linkage really directly proportional to each other, because the only difference is that flux linkage means there's not just one winding. You multiply by n. Now it starts here at a maximum and it goes all the way to 0 when it's here at 90 degrees. And you can see that it goes gradually down to 0 there at 90 degrees. We're not going to look at the gradient yet, but we will just now. Then in this position, it's going to a maximum again, and then it's going down again, and then it's going to a maximum again. So I think that graph makes sense to most of you. because you can just look at the number of lines passing. Now, Faraday's law says that EMF is directly proportional to the rate of change of magnetic flux or magnetic flux linkage. And then you'll remember that if we want to change this to an equal sign, there's also that you have to add the negative to the equation there. Now, if you look at this graph and you think about your math that you know, change in phi over change in t is basically change in y over change in x. So that means the gradient of this graph, the gradient of your phi graph, will give you the shape of your EMF graph. So that is why the gradient was included in this diagram. So if you look here, we start here at a maximum flux, but the gradient here is 0. So the gradient there is 0. Then it goes steeper, 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 steeper. And at that point, the gradient is a maximum and it is positive. Yes, it is positive. Now we can carry on. Up to this point here again, the gradient is 0, and here the gradient is a maximum again. The people that are doing AP maths understand this quickly because you do the derivatives, but it doesn't matter. You don't need AP maths to do this, but you can think about it in that way as well for those people. So now, if you have a flux graph, you can easily now go and draw the EMF graph, because you now know that where this one starts here, the gradient is 0. So if I need to draw an EMF graph, and I'm not going to use this one because I don't like the direction. Let's show you why I don't like the direction. If you look at this one, here the gradient is 0. So your EMF graph will start at 0. That is perfectly fine. But then you will see that your gradient is getting steeper, 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 positive. So yes, your EMF should be going up, 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 but it should be, because of Lenz's law, that negative sign, it should be going in the negative direction. So let me just draw it on this one. So if I'm drawing the EMF, it should be going down, 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 down. And here at 90, I'll have my maximum positive gradient here, but it means that my EMF, remember, is going to be the negative of the gradient of the phi graph. So you're going to get a negative value here. Then you're going to go there up to 0 again. And you're going to go down. So it will just be actually the opposite of this one that we had here before. All right, this one is absolutely right. So I'm just going to quickly get rid of the ones I don't like here, and then we can talk through it again, because I think it's always needed to say this twice. Look at this little graph here. You can see that for this one here, you can see that there your flux starts at a maximum. They've decided that it's positive. It goes the same, similar thing. Now, if you look at your EMF, this one has a negative gradient. Therefore, your EMF will start in the positive direction because of Lenz's law. So here, my gradient is 0. So my EMF starts at 0. Here, the same here. Now, the only thing why I put this graph in here originally was because you need to be able to see, what if I'm now going to turn this faster? You need to realize that if I turn it faster, my flux is going to change faster. So you'll have twice the rotation rate. But because of the direct proportion from Faraday's law, we know that EMF is directly proportional to the rate of change in magnetic flux. Now, if you look at this one, if the time goes down, which means I'm turning faster, the EMF value must also go up. So yes, I'm going to have more of these little waves, but I'm also going to have a higher EMF. So please remember, if they ask you to redraw a graph for faster rotation, the flux will have the same value. That's not changing because that is to do with the magnetic flux density that hasn't changed. So the magnetic flux, the change in magnetic flux is still constant. So your values here will stay the same. But instead of having one turn, you're now having two turns in the same amount of time. But when you look at your EMF graph, this one is perfectly drawn from here, then you'll have double the amount of rotations, but you'll also have a higher EMF. Just keep that in mind as well. Now the only thing left is rectification, and let's just do it in this video, then it's all done. Now for rectification, you need to understand what a diode is. Now a diode in your SAGs also, it explains that a diode is something that only allows current to flow in one direction. So I'm going to use, and please use a highlighter in the exam when you get a question like this. Because if you go and you say, all right, I've got mine, just make it a little bit thinner, I have my current here, conventional current goes from positive to negative. Now the diode in your circuit is that arrow that you see there. So in this one, the arrow points towards the right. So what that means is the diode will only allow current to flow that way. So for this first circuit, the diode is connected. They call it forward bias because it is connected perfectly. It lets the current flow and my light bulb will shine. If you look at this circuit, when the battery is swapped around, now the current is still conventional current, still from positive to negative, but now follow the path from positive to negative. And you will see, oops, I can't go through. So that straight line that you see. So for a diode, you'll always have the arrow. This is the allowed direction. And then you'll have the line there that shows the not allowed direction. So that's your symbol for your diode. Now in this one, the current will not flow because remember, if there's a block somewhere in the current, there will be nothing happening. So this light bulb will not shine. So if I have a generator, and this generator has now produced an alternating current for me. So this is my input, and I put a diode in my circuit. This is the first way of changing an alternating current into a direct current, which we often need because when you're charging something, you need a direct current because remember, even from electrochemistry, you can't give an electron, take an electron, give an electron, take an electron. So if you want to charge a battery, you need direct current. So that's one of the things that need direct current. But if you now look here, this is our input. So what for our input, the current goes positive, negative, positive, negative. So that is what my generator is providing. But now let's see. Remember what an alternating current does. So let's go from positive. Like I said, follow the line. It makes your life easy. So here you go. So for that pink cycle, we're all happy. The current is flowing because it's going in the direction in which the diode is allowing the current to flow. So this little bit will be there. Okay, you'll see that. Now so this is what your resistor will, I always say see, but this is what your resistor will experience basically. Now if I take the other way, now remember when the current stops around, they always only give you one. But remember, an alternating current, that doesn't stay positive. Now for the next cycle, this becomes positive and that becomes negative. So if I go and do the other way, now from positive to negative, so for my green cycle, I go this way around and you'll see, oops, stuck again. So I can't get through this way. So this little bit here, this green bit, will not be there. And so on. So what you see as an output will be this waveform here. So you will see you don't have these bottom parts, they're gone. So the diode is not allowing the current to flow in that direction. So what we have done is we have changed an alternating current into a direct current. And that is what rectification is, when we change an alternating current into a direct current. This type of rectification, though, is only giving me back half my wave, and therefore it's called half wave rectification. Because I'm missing that little bit there at the bottom. But please remember that these rotations happen so many times per second that your brain can barely see that. If you're looking at a light that is rectified, you wouldn't see that. You can even take yourself in slow motion, look at the light in your house, and sometimes you can see the flickering if you do a slow motion, but you can't see it by naturally just looking at the light. So that's the one form of rectification, which is half-wave rectification. Now we do want full-wave rectification as well, and therefore we can now change this whole system. Let me just move these out of the way for us again. And we can use what we call a bridge rectifier. Bridge rectifier is just 4 diodes, and they don't have to be connected like this. There are many ways in which they can be connected. So please, when you get a question like this, again, follow the path with your highlighter. So the input looks like this. We've got AC coming in. You have your alternating wave there. Now, if you take, let's say in our first cycle, this is positive and this is negative. Take your highlighter and we follow the path. So we go from positive to negative. Now here you will see I cannot go this way because my diode blocks it. Here I can go that way. I cannot go this way. And here I go, meaning that this first little bit here, my resistor or anything that you put here, your cell phone charger, is now seeing this little bit or observing or experiencing. They're not real. Remember, they're not alive. I always say see, but they don't have eyes. Now here we have to, when you see that little thing there, it means it goes over the other wire. So it goes over the other wire. It will not go there because it's not going to go from positive to positive. So it's not going to go back this way. Therefore, it will go there and back to negative. So what my resistor, if there was a resistor here, the resistor gets the current in this direction for this first little bit. Now you do the second one. Let's see. Do exactly the same. So for the second one, we're going to swap. We're just going to say this is now positive and this is now negative. So let's take our highlighter again. We go from positive. Here we're going underneath there. Where are we going here? We can't go this way. So we're going up. Can't go that way. So we're going directly back here. Sorry, squiggly line, but wires can be squiggly. When I get here, can you see what's happening? My current is flowing in the same direction as it did before. So my output, my resistor or my light bulb or my cell phone charger is getting this in the positive direction again. Now I just have to follow the path. I'm going over there. This time I'm not going to go back because I'm not going positive to positive, remember? So I need to use this path here and get back to the negative side. And that is a bridge rectifier. So again, it's changed our AC to DC. So we've converted alternating current into direct current, and that gives me full wave rectification. Now I am quickly going to mention one other way in which you can get full wave rectification. If you are looking at a generator, now if I look at this generator here, I think I need some space. Clean up. Now, if I look at that generator there, You know now how it functions. I don't have to tell you that anymore. Otherwise, you just have to go and look at the videos again. So if you look here, if this was a generator that you are used to, there would be slip rings. With slip rings, the generator will supply positive when moving up, negative when moving down, positive when moving up, negative when moving down. So you will get this type of wave always from the generator. If you see slip rings there, it's a normal generator and it's going to produce alternating current. If you don't see the slip rings there and you see a commutator, the commutator will do the same job as the four diodes. And it will change, remember, from a motor, a commutator changes the direction of the current every half a turn or every 180 degrees. And it's going to do exactly the same here. So that will be there, but as soon as the current goes negative, it will change it. So you'll get the first little bit positive and the second bit positive. So now this generator doesn't provide me with AC anymore. It provides me with DC. So the current was already rectified as it's leaving the generator. And therefore, this will be called a DC generator, which is not really in your syllabus, but it's also a form of rectification because I've now changed my alternating current into a direct current. Again, there's a little YouTube video there that you can watch. And the only thing that we have now left is to look at some past paper questions. And that again will be in the next video.